Hello, good morning once again. This is Sir Mike. Today we're going to discuss solving exact differential equations using the second method. So these are the steps in solving exact differential equations using the second method. If you notice, these steps are quite similar to the steps in solving exact differential equation using the first method. So the first step is you need to identify your m of x and y and n of x and y in the differential equation, and you need to test the exactness of the differential equation. Then the second process is you need to integrate n of x and y with respect to y. In the previous method, you are integrating m of x and y with respect to x. So that's basically the difference between the first method and the second method. So our base function here is n of x and y. Now, the third step is you need to differentiate the result in step 2 with respect to x. Then after that, you equate the result in step 3 to m of x and y to get g prime of x. While in the first method, you are performing this fourth step in order for you to get g prime of y. Next step is you need to integrate g prime of x to solve g of x. Then after solving g of x, then you need to write the general solution based on the result in your second step. So let's try to recall the first step, the first method in finding the solution of exact differential equations first, so that you will be refreshed with the process, and then you may compare the steps of the first method to the second method that we'll be discussing this morning. Okay, so we're going to apply the first method here. So we have the differential equation, y squared minus 2xy plus 6x dx minus the quantity of x squared minus 2xy plus 2 dy is equal to 0. So the first step is you need to test whether the differential equation is exact or not. So we identify first your m of x and y, and this is y squared minus 2xy plus 6x. And then you need to get the partial derivative of m with respect to y. So here, the partial derivative of y squared with respect to y is 2y. While here, on the second term, your 2x is held constant, okay, and then the derivative of y is 1. Therefore, the derivative, partial derivative is negative 2x. While your 6x here is held constant. So, and you are aware that the derivative of a constant is 0. So, the partial derivative of m with respect to y, in this case, is 2y minus 2x. Now, let's proceed to the other function, that is n of x and y. So, n of x and y here is negative x squared plus 2xy minus 2. We need to solve the partial derivative of n with respect to x. This is how we are testing the exactness of the differential equation. So the derivative of negative x squared, the partial derivative of negative x squared is negative 2x. And since your y is held constant, okay, the derivative of 2x is 2. Therefore, the partial derivative of 2xy with respect to x is 2y. Then, anyway, your negative 2 is constant. The derivative of that is 0. So if you notice, your partial derivative of m with respect to y is equal to your partial derivative of n with respect to x. So we can therefore conclude that the differential equation is exact. Okay, the next thing that you need to do is to integrate your m of x and y with respect to x. Take note, we are discussing here the first method. Okay, so the integral of y squared minus 2xy plus 6x with respect to x will give you y squared. You treat y squared as constant times the integral of 2 dx minus 2y, because you treat negative 2y as constant, times the integral of x dx plus you factor out also 6 because that's constant, times the integral of x dx. So you have the integral of dx as x, Then you have the remaining expression, that is y squared. So you have xy squared minus definitely the integral of x dx is x squared all over 2. So you have negative 2y x squared all over 2 plus 6 times the integral of x dx is x squared over 2. So you have 6x squared over 2 plus, of course, the function g of y. The reason why we are adding here your function g of y is because in our integration process, we are only getting the integral with respect to x. Okay, so we are adding here uh, the function g of y. So instead of having a constant to be added in the expression, we need to add g of y. Okay, so our answer would then be xy squared minus x squared y plus 3x squared plus g of y. Please take note of this expression because we will be using this expression for our general solution. That is, we need to equate this to 0. So the main aim here, or the main purpose here, is for us to solve first for g of y. Solve first for g of y. Okay, so the next step that we need to do is to get the partial derivative with respect to y. The partial derivative of the result with respect to y. So you have partial derivative of xy squared minus x squared y plus 3x squared plus g of y. So your x is held constant here. You take the derivative of y squared, that is 2y. So you have your 2xy. And again, in the second term, your x squared is held constant. You get the derivative of y, that is 1. So you have negative x squared plus your 3x squared is constant. You consider your 3x squared is as constant. So the derivative of that is 0. So the next thing that you need to do is to get the derivative of g of y. Hence, you have g prime of y here. You have 2xy minus x squared plus g prime of y. Next, we're going to equate the result, that is 2xy minus x squared plus g prime of y, to your n of x and y. And if you notice here in our equation, there is negative 1 outside the parentheses. You need to distribute first the negative symbol here inside the parentheses. So you'll be having negative x squared plus 2xy plus 2. So if you notice here, you have 2xy minus x squared plus g prime of y is equal to your n of x and y. After distributing negative 1 inside the parentheses, you have negative x squared plus 2xy minus 2. Minus 2. So you cancel out similar terms. You have 2xy here on the left side of the equation, as well as on the right side of the equation. So you can cancel that out. Next is you have your negative x squared in the left side of the equation. You can also find negative x squared on the right side. You can cancel that out. You are left with g prime of y is equal to negative 2. You take the integral of both sides. So you have integral of g prime of y is equal to negative 2 times the integral of dy. We are integrating with respect to y. So the integral of g prime of y is g of y, and that's equal to negative 2 times the integral of dy is y plus the arbitrary constant c. And if you can recall our process, in step 2, we're able to find an expression that can be equated to 0 that will become our general solution of the differential equation. You have xy squared minus x squared y plus 3x squared plus g of y. Since we are already done with the process of solving g of y, we can now substitute g of y in our equation. Xy squared minus x squared y plus 3x squared plus g of y is equal to 0. So you substitute g of y with negative 2y plus c. So you have xy squared minus x squared y plus 3x squared minus, this time you have 2y plus c is equal to 0. Or you can rewrite it this way. Xy squared minus x squared y plus 3x squared minus 2y is equal to capital letter C. Okay, you transpose positive C to the other side. That will give you another constant. You can represent that with C, capital letter C, or C sub 1. Next, we apply the second method here in this differential equation. So I labeled here, I labeled this example as example number 1. So you have the quantity of 2xy minus 3x squared dx plus the quantity of x squared minus 2y dy is equal to 0. So the first thing that you need to do is to test the exactness of the differential equation. I will not going to show to you the process already because I discussed the test of exactness in our previous lesson, and I also presented the test of exactness in our previous example. So let's proceed to step 2 or step B. The next thing that you need to do using the second method is to integrate n of x and y with respect to y. If you notice, in our first method, we are integrating m of x and y with respect to x instead. But here in this second method, we are integrating n of x and y with respect to y. So we get n of x and y. You have x squared minus 2y. We integrate with respect to y, so you have integral of x squared minus 2y dy. You treat x squared as constant. You factor that out times the integral of dy minus 2, that is constant, times the integral of y dy. So the integral of dy is y. So you have x squared y minus 2 times the integral of y dy is y squared all over 2. So you have x squared y minus 2y squared all over 2 plus g of x. Okay? So in our first method, we are adding g of y. But here in our second method, we are adding the function g of x. So you have x squared y minus y squared. That is after canceling out 2 in the numerator and the denominator of the second expression plus g of x. Okay, so the next step is you need to differentiate the result with respect to x. So the derivative of x squared y minus y squared plus g of x with respect to x is, of course, here y is held constant. You factor it out, take the derivative of x squared, that will give you 2x. Hence, you have 2xy. And your negative y squared is treated as constant. And you are aware that the derivative of negative y squared, since that is constant, that will be equal to 0. So you add instead g prime of x. The next thing that you need to do is to equate the result to m of x and y to get g prime of x. So you write here 2xy plus g prime of x. That's equal to your m of x and y, which is 2xy minus 3x squared. So you can cancel out your 2xy in both sides of the that is found on both sides of the equation. So you're left with g prime of x is equal to negative 3x squared. Then after that, you need to solve the integral. So your g prime of x is equal to negative 3x squared. The integral of g prime of x is equal to negative 3 times the integral of x squared with respect to x. So the integral of g prime of x is g of x. And this is equal to negative 3 times the integral of x squared, that is x cubed over 3, plus the arbitrary constant c. And you simplify the expression, so you can cancel out 3 in the numerator and the denominator of this expression. So you have here g of x is equal to negative x cubed plus the arbitrary constant c. Then after that, you can now write the general solution. You have your x squared y minus y squared plus g of x is equal to 0. So we are done solving g of x. We need to replace g of x with negative x cubed plus c for our general solution. So you have x squared y minus y squared minus x cubed, that x cubed plus c, that is our g of x already, and this is equated to 0. Or you can simply rewrite it this way: x squared y minus y squared minus x cubed is equal to 0. Now, the reason why we are discussing method 2 is that there are some instances wherein our exact differential equation is written this way, in this form. Meaning to say, as you can see in the differential equation, your n of x and y is more simple than your m of x and y. Using the first method, you need to consider your m of x and y as your starting function. But in the second method, you are considering your n of x and y as your starting point. So in this case, you can see that m of x and y is more complex than your n of x and y. So we need to start with n of x and y. And of course, in doing that, we need to apply the second method. Okay? So the first thing that we need to do is to test the exactness of the differential equation. Your m of x and y definitely is equal to cosine of x minus x sine x plus y squared. Then take the partial derivative of m with respect to y. So your cos sine x is treated as constant, and so with your negative x sine x, so these are all constant. So the derivative of a constant is 0. Now, you take the derivative of y squared since you are getting the partial derivative of m with respect to y. That will give you 2y. Next, you consider your n of x and y is equal to 2xy. That's your n of x and y. You take the derivative of n with respect to x, that is 2y. Therefore, we consider the differential equation as exact because the partial derivative of m with respect to y is equal to your partial derivative of n with respect to x. Now, you get the integral. The integral of 2xy dy with respect to y is, you need to treat your 2x as constant. So you factor that out, then you take the derivative or the integral rather of y dy. So the integral of y dy is y squared over 2. And then you include your x also. So you can cancel out your 2 in the numerator and the denominator. Plus, of course, you will be adding the function g of x. So you have your xy squared plus g of x. Take note of that because you will be using that expression. You equate that expression in to 0 in order for us to get the general solution. Then after this, you need to get the partial derivative with respect to x. So you have xy squared plus g of x. So the partial derivative of xy squared plus g of x uh, with respect to x is, of course, you're treating your y squared as constant here. You take the derivative of x, that is 1. So you have your y squared plus the derivative of g of x is g prime of x. Then you need to equate, after that, you need to equate your result or your y squared plus g prime of x to m of x and y. And in our example, our m of x and y is cosine x minus x sine x plus y squared. So you have the equation y squared plus g prime of x is equal to cosine x minus x sine of x plus y squared. You can cancel out your y squared in the left side of the equation and on the right side of the equation. So you're left with g prime of x, and that's equal to cosine of x minus x sine of x. The next thing that you need to do is to get the integral. So the integral of g prime of x is equal to the integral of cosine of x dx minus the integral of x sine x dx. There's no problem with the integral of cosine x dx because you can solve that directly. The integral of cosine x dx is sine x, but there's a need for us to apply integration by parts in getting the integral of x sine x dx. We assign, if you can still recall the process of finding the integral of functions using integration by parts, you assign your u and then your dv. So our u here is your x, and then the derivative of x is dx. Our dv here is sine of x dx, and the integral of dv is negative cosine of x. Okay, so you have the integral of g prime of x, that's equal to sine of x minus, of course, you plug in the values or the expressions. representing the equation or the formula, that's uv minus the integral of v du. So our u here is x times your v, that's negative cosine of x, minus the integral of v, that is negative cosine of x dx. Then after that, we have sine of x plus negative 1 multiplied by negative cosine x, that will give you positive cosine x. And of course, you have your x here. So plus x cosine x minus, you multiply first your negative 1 by your negative cosine x. That will give you positive, okay, positive cosine x. But you're getting the integral of cosine x, that will give you negative sine x plus c. You cancel out terms. You can cancel out sine of x and negative sine of x. You're left with your g of x is equal to x cosine of x plus c. We can now rewrite the general solution because we are done solving for g of x. So xy squared plus g of x is equal to 0. And you replace your g of x with x cosine x plus c. Okay, so xy squared plus x cosine x plus c is equal to 0. Or you can rewrite it this way. Xy squared plus x cosine x is equal to c. Or you can have xy squared plus x cosine x is equal to c sub 1.